All right, part 2 of today's lesson. It's simplifying radicals. A lot of this is review, I hope. An important piece of simplifying radicals is knowing your perfect squares. I'm going to fill this chart out real fast, but it is expected that you know at least the first 12 perfect squares. You will have a hard time if you don't know at least the first 12, but knowing more than just the first 12 does have its benefits. I hope. Let's see here. See if I even remember the ones up here. And there's some other important ones in here as well, but these are certainly some of the ones that are the most helpful to remember. The reason being, like 5, 12, 13, that's one of your triples. So like 12 squared and 13 squared, that's part of 5, 12, 13. 8, 15, and 17, that's another big one. Like just knowing that 17 squared is 289, like you see a 289 in a problem, like you know that's going to lead to 17. That can save you a bunch of time, knowing that it's probably going to be an 8, 15, 17, or possibly, I should say. And then 7, 24, 25, another big one. So it's not like you have to know those, but it can be helpful. I mean, I've told you guys all year in math, the more you know, the easier math is. So let's talk about simplifying radicals. Square root of 8. There's a few approaches. I'm going to show you all the approaches. The first approach is my favorite, and it is called perfect square factoring. That's the whole reason that you need to know these, is you're looking for factors that are perfect squares. Well, 8 could be 1 times 8. It could be 2 times 4. This one involves a perfect square. Anytime factors involve a perfect square, that is a good way to go. So I'm going to write this as the square root of 4 times the square root of 2. So the root 8 becomes root 4 times root 2. Well, why did we do that? What is the square root of 4? The square root of 4 is the whole number 2. What about the square root of 2? That's not a whole number. That's about 1.4. You have to leave that as root 2. Root 4 becomes the whole number 2. Root 2 cannot be simplified anymore. There's no perfect square factors. There's nothing else you can do to the square root of 2. So that's done. Another way you could do the same problem, square root of 8. So a lot of teachers tell you to break it down into their prime factors. So instead of stopping at root 4, you would keep going, right? So you would keep breaking it down, and what you have here is root 2 times root 2, which is 2, and then another root 2 off to the side. So some teachers tell you to make a prime factorization tree. So those would be the two main ways that you could factor this. You do all the prime factors, and you know that if you have the same radicand twice, that pair becomes a whole number of that radicand. So root 2 becomes whole number 2. All right, let's go look at number 2 here. The square root of 32. If you're doing perfect square factoring, you actually have two choices, but the best choice is root 16 times root 2. The square root of 16 is whole number 4 times the square root of 2, not a whole number. And that is complete. That's the whole thing. So if you saw that root 16, awesome. That's the fastest way to do it. But you don't have to see the biggest whole number. So what if you didn't see 16, but you saw root 4 times root 8? Awesome. The thing is, you're not done. Here we know that root 8 also has a perfect square factor. So now we break up the root 8 into perfect square 4 and 2. And you can think of this a couple ways, but root 4 is 2. So root 4 becomes 2, whole number 2. Root 4 becomes whole number 2, and then you have a square root of 2. Well, 2 times 2 is 4, and then you have a root 2. Same answer we just got. Or, if you have a keen eye, what is root 4 times root 4? That is whole number 4. So there's a couple ways you could think about that. And then if you did it the first way that I showed you, or not the first way, the second way that I showed you, the square root of 32, you could break that down into root 2 and root 16, which I would hope you recognize that as 4 right there. But if you keep going, if you keep breaking down, that'd be root 2 and root 8, which is root 2 and root 4, which is root 2 and root 2. Ooh. So what do we have here? We have root 2 times root 2, that is whole number 2. Root 2 times root 2, that is whole number 2. And then we have another radical 2. So we have whole number 2 times radical 2, which is whole number 4 times radical 2. It doesn't matter which way you pick, they all end up in the same place. How about the square root of 18? What is a perfect square factor of root 18? Well, root 9 is the biggest perfect square, really it's the only perfect square factor of root 18. And what is the square root of 9? It is whole number 3. So we break up root 18. Just a little piece of advice. I see this pretty often. Happens every year. Someone does root 18 and they break it up into root 2, root 9. They put root 2 first and root 9 second. And then they tell me the answer is 2 root 3. I see this really often. It's just the way our brains are wired some. Like we know this is 3 and we have the 2. And what we do is we just drop them straight down. Like we keep them in the same column. Even though we're doing the square root of 9 and making it 3, we go ahead and we put it in the root because that's what's right below it. And that's the way our brain kind of is wired some people's brains. That is not correct, right? Root 9 is whole number 3. And then you have a radical 2. So that is 3 root 2. It shouldn't matter which way you write it. So to avoid that, maybe always just write your perfect square on the left side. And that way it does just drop down to the left side. Square root of 72, I'm not going to do every way. I'm going to do just the fastest way. The biggest perfect square is root 36. The square root of 36 is 2. So you could have, I'll do one more way. You could have done the square root of 9 times the square root of 8, which is not done because the square root of 8 is root 4 times root 2. You are not done until you've pulled out every possible perfect square. So like here I was done because there's no more perfect squares that go into 2. But here I was not done because 8 has a perfect square factor. And what we have here is the square root of 9 is whole number 3. This is whole number 2. And then this is root 2. That is 6 root 2. This is okay. If you don't see 36, I would rather you just pull out the 9 and be doing something than sitting there trying to find a bigger number. You might sit there a long time and never find the bigger number. I would much rather you just pull out the one you see other than hoping to find a bigger one. I see people every year sitting there, 1 or 2 minutes or more trying to think of numbers that are bigger than the one they already have, and then they waste a lot of time when they could have just finished the problem. Yes, it's a little bit more work, but just do it. All right, so all of this is stuff like you've done before. None of this was brand new. This is newer. Remember, this is a non-calculator quiz we're going to have over all this. So we have to have good strategies. I do not expect you to do 21 times 35 and simplify that number, right? That would be like 385. No, I'm not asking you to simplify root 385. That's no. So what do? Well, remember, you can multiply in any order. So I'm going to do whole number times whole number. So that's 7 times 3, that's 21. And then I'm going to focus on the radicals. And in this class, I've told you all year, it is better to break down first, then rebuild, than it is to build and then break it down. So I'm going to break down these two radicals. And I'm looking for common factors. We want to GCF it. This is root 7 times root 3. This is root 7 times root 5. Now, why did I do that? Why did I break those two numbers down? Why just the GCF? Because what is root 7 times root 7? That is whole number 7. So we pull out the GCF, and then that'll cancel out the radical for those two numbers. Root 7 times root 7 is whole number 7. But we may not be done. Make sure you focus. Root 3 times root 5. Are there any more common factors? Maybe 7 wasn't the biggest one, and maybe there's another common factor to pull out. Are there any perfect square factors? We're looking for all of this. The answer is no. These are both prime numbers. They don't have any of that, so we just multiply them back together. Root 3 times root 5 is root 15. We have whole number 21 times whole number 7 would get you 147 times the square root of 15. And that's it. Let's do another one. Okay. We're going to start, I do whole number times whole number. 5 times 3, I get 15. Right? So those are gone. And then I break down. I'm looking for the GCF. 20 and 35 has a GCF of 5. So I'm going to pull out a root 5 from each of those. And what is root 5 times root 5? Well, it is whole number 5. So those are gone. And then we have root 4 times root 7. Are there any more common factors? Are there any more perfect square factors? And yeah, root 4 actually is a perfect square itself. So what is the square root of 4? It is 2. So root 4 becomes whole number 2, and we're left with a root 7, which can't be broken down. Then what would be the best way to multiply this? I would do 5 times 2 is 10, and then do 15 times 10. Oops, times root 7. There we go. I'm going to do another one. 4 root 24, 5 root 48. I'm going to do this one 2 different ways. First, I'm going to do it the fastest way. 4 times 5 is 20, right? So I take care of those. And then what is the GCF? It's not 2, it's not 3, it's not 4, it's not 6, it's not 8, it's not 12, it's 24. All those others were options, but the GCF is 24. So I'm going to leave this as root 24, but I'm going to break this into root 24 times root 2. And what is root 24 times root 24? Well, it's just whole number 24. And we're left with a root 2, leaving me with 480 root 2. I don't always expect you to see the GCF correctly, though. So let's try it again. So it's 4 root 24 times 5 root 48. What if you thought the GCF was a different number, like 12? That's fine. 5 times 4 is 20, right? We still take care of that. But let's say you pulled out a root 12. Well, when we do root 12, we have root 12 times root 12, so we have it times 12. So those are gone. But then what do we have here? We have root 4. And what is the square root of 4? Well, it is 2. So didn't we get back to the exact same thing, 20 times 24, with a leftover root 2? Yeah, it's the same answer. It's the same answer. And it doesn't matter what you pulled out. You were going to get the same answer as long as you keep doing the process correctly until you can't do it anymore. 2 has no more perfect squares. There's nothing left I can do to the number 2. All right, how about this one? I'm going to do 6 times 3, that's 18. Those are gone. And then what's the GCF for 20 and 32? I think it's going to be 4. So root 4 times root 5. This is root 4 times root 8. Well, what is root 4 times root 4? Well, that's going to be times 4. So those are gone. Do we have any more things we can do? Look at these two numbers. Is there another GCF? Like if 4 wasn't the biggest GCF, there might be another GCF. Could I pull out the number 4 or sorry, number 5 or anything like that? No, there's no more GCF. Are there any more perfect squares involved? And yes, root 8 is root 4 times root 2. So we had to break down root 8. Well, what is the square root of 4? The square root of 4 is 2. Square root of 4 is whole number 2. And then we still have root 5 and root 2. Do they have any common factors? No. Do they have any perfect square factors? No. Well, then all we can do is multiply those back together. So root 5 times root 2 gives me my root 10. And then here we got to multiply. I would do 18 times 2 is 36. And then 36 times 4 would be 36 times 2 times 2. 36 times 2 would be 72, times 2 would be 144. All right, let's talk about division, and then we'll wrap this up. So List numbers that are equivalent to 2/3. We need to understand how this works. There's a lot of choices. 4/6, 6/9, 8/12. I could keep going on and on. All of these, when you type them in the calculator, they will be 0.6 repeating as a decimal. That's what they all are. Why? How does that work? How can all these things that look different all be the same thing? Well, how do I go from 2/3 to 4/6? What do I multiply by? Oh, you multiply by 2. No, you don't multiply by 2. You multiply by 1. What do I mean? You're multiplying the top and bottom, the numerator and denominator, by the number 2. Well, what happens when you multiply the top and bottom by 2? Look at this. What is this? If I just said, what's 2 divided by 2? What is that? That is 1. So what you're actually doing is multiplying by the number 1. Right here, you would multiply by the number 1. It's just this time it was times 3 times 3. So a big part of high-level math is finding unique ways to write the number 1, because you want to change how something looks without changing its value. How do you do that? You multiply it by a unique version of the number 1. So this and this are the exact same number. How do I know? Because I multiplied it by the number 1. So that's why it didn't change value. In a fully simplified fraction, what has to be in the denominator? Positive whole numbers. And whole numbers by default have to be positive, but I need to emphasize positive whole numbers. 7 divided by -2 is not simplified. You would need to multiply the negative to the top. That's the simplified answer. And there's a lot of people that would argue that it doesn't matter. I disagree. I think it does matter. I think this is the best version of the number. I think there's a few reasons why. I'm not going to get in a big argument on that right now, but I will say that just by the rules of division, it doesn't make sense. Can you take $7 and divide it among -2 people? Division means to divide among. I can't take $7 and divide it among -2 people. Can I take a loss of $7 and divide that among 2 people? Yeah. 2 people could both owe $3.50. I could do that. So this is the output your calculator would give. Your calculator would never give that. That's not an output. It would never leave a negative in the denominator. Also, like if I had 5 divided by the square root of 7, right? That's not a whole number, right? 5 divided by, that's almost 3. So I don't know, 2.8, I don't know. Can you do $5 divided by 2.8 people? You can't do it. You can't do it. So that's not simplified. You need positive whole numbers in the denominator. Why am I saying all this? I'm going to ask you to simplify this. Now, I know that not every test makes you simplify these, AP tests, things like that. I know that. But I do think it's important. This is not the best version of this number. It's like 7 plus 3. When you were in 2nd grade, you were asked to simplify 7 plus 3, and you said it equaled 10. And because 10's the best version of that number. You don't want to go around and say, hey, I got 7 plus 3 bananas. You'd go around and say, I have 10 bananas. That's the better way to say it. Well, there's a better way to say 5 over root 3. And it may not make a lot of sense right now, but the more math you do, the more it will start to make sense that there's a better version of this number. How do I get rid of a square root of 3 in the denominator when I cannot change the value? I need to multiply by the number 1. Right? Just look at this real quick. What is the square root of 3 divided by the square root of 3? That is 1. We're doing times 1. But what's the result? You get 5 root 3 on top. What is root 3 times root 3? It's the same radicand. What is root 3 times root 3? It is whole number 3. This is the better version of the same number. They're equal. Those are the same number. But this one is better and it is simplified. You could also write it as 5/3 root 3. That's the same thing. 5/3 root 3, that's just as good. They're the same. 7 divided by root 10, I multiply by the number 1. Gets me 7 root 10 on top, whole number 10 on bottom. Nothing else I can do there. That's the best version of that number. There is a pattern. If you notice, like if I said 3 divided by root 7, that would be 3 root 7 over 7. If I said 10 divided by root 11, that would be 10 root 11 over 11. The radical swings to the top and cancels out on bottom. The radical swings to the top and cancels out on bottom. The radical swings to the top and cancels out on bottom. The radical swings to the top and cancels out on bottom. Knowing that can make these go a lot faster. So like this one, I know without even having to write it out that the radical is going to go on top and cancel out on bottom, and then I have to reduce, right? This is like 7/14 times root 14. Well, 7/14 is 1/2. So root 14 over 2 is the better way to write that. If you stop here, you're going to be wrong. It's not fully simplified. You need to make it all the way to this to be fully simplified. Here, I'm going to reduce first. I'm thinking this is the fraction 4/8 and the square root of 12/24. These are the same thing. What do those become? This becomes 1/2. This becomes the square root of 1/2. I don't write this out every time, but this is how you're thinking about it. So what do I have on top? I have a 1 and a square root of 1. What do I have on bottom? A 2 and a square root of 2. Well, let's clean that up. What is 1 times root 1? Well, that's just 1. And then 2 root 2. Can I leave the square root of 2 on bottom? No. I'm going to have to multiply by the number 1. I'm going to write it out again just so you can see it, but I'm not writing that out every time. The radical swings to the top, 1 times root 2, and cancels out on bottom. But let's look here real closely because there's already a 2. Root 2 times root 2, that is 2. But don't forget, it's 2 times the 2 in front, giving you an answer of 4. And that is done. Can you reduce this? No, that is radical 2. That is not a whole number. Divided by whole number 4. Can you take a radicand and divide it by a whole number? No. You can't do anything with those. And I know I'm going kind of quick. Let's look at this from the beginning. Let's say you're just looking at it like this. You could think of 4/8 as becoming 1/2 and 12/24 as becoming 1/2. These can reduce because they're whole number with whole number. These can reduce because they're radicand with radicand. That's where I got this. So let's do it again. This one looks a little funky, but we can rewrite this as 7, actually we can go ahead and reduce it. Like if I just said reduce 15 over 18, what would that become? That would become 5 over 6. This is 5 over 6. So that we could rewrite this as 7 root 5 over root 6. If you have a fraction inside of a radical like that, you can break it apart into 2 separate radicals. And then it's times 7, so I put a 7 in front. I swing the root 6 to the top, giving me root 30, and it cancels out on bottom. So I reduce, then it's called rationalizing the denominator. All right, here's another one. Nothing here reduces. This looks a little messy though. I'm going to think about this as being 3 root 2, those are my numerators, and 4 root 15, those are my denominators. Nothing reduces. Nothing, I can't clean anything up. Root 15 has no perfect squares. Root 2, there's nothing to clean up. There's nothing to do other than we got to multiply the root 15 to the top. I'm going to go ahead and write it out one more time. This is what I'm doing. I'm multiplying root 15 over root 15. That gets me 3 root 30 on top. But on bottom, I have root 15 times root 15. That is 15. And don't forget the 4. I have 15 times 4. That is 60. Can I reduce anything here? Yes. 3 and 60 reduce. So this becomes root 30 over 20. 60 divided by 3 is 20. What are the 4 most common triples? Pause the video and try. Boom. All right. See if you got them right. Guys, that was a lot of stuff. Good luck. Come ask questions if you got them.